Hello everyone, my name is Hakan Güleş. I'm the team leader of the Starloop team. I'm also a graduate student and research assistant at Yıldız Technical University, where our team is located. Today we are going to present our levitation system to you, but first of all I would like to introduce our team briefly. The Starloop team consists of 6 departments within itself. Analysis team, in which electromagnetic and strength analyses are made with the finite element method. Mechanical team is that designs, manufactures, and assembles the capsule. Electronics team is that select electronic components, designs circuit boards, and makes sensors and actuator work. Communication team is that provides communication with the capsule and telemetry with appropriate protocols and develops the user interface. Control team is that responsible for air gap control of levitation system and the vehicle with proper precision while it's running via modeling and control methods. And finally, coordination team, which deals with the coordinated functioning of the team and project management, and more importantly, finds the necessary funding to be able to continue our work. Many of our team members are among us as listeners at the moment, very excitedly for attending this conference. I will present the levitation system, but maybe they can join us at the question and answer section. So let's get started. Before going to the technical details, I would like to talk about how we started to design the system. If you want to levitate a capsule, in other words, cutting the mechanical contact of it from the ground, you need to obtain a lift force that will overcome gravity. This force can be obtained by using various suspension methods. For example, drones successfully do that by using aerodynamics. However, it can be done in 2 ways by dealing basic electromagnetism, which are electromagnetic suspension and electrodynamic suspension. The main difference between the two is that in one you need a ferromagnetic rail, in the other a conductive surface is sufficient. We wanted to design our system with electrodynamic suspension method because the rail in the tunnel where the pod will move is designed by using aluminum material, which is conductive but not ferromagnetic. Although different electrodynamic suspension methods may have been used, the Starloop's levitation system is designed based on electrodynamic levitation method, which uses permanent magnets instead of coils and birotary Halba array rather than linearly. In this way, the system can be levitated even in the first place, without having to exceed a certain speed. So now we understand the working principle of our system. How can we do that? The purpose of the electrodynamic suspension system is to create eddy currents in the conductive plate by creating variable magnetic fields against the non-ferromagnetic conductive plate and to generate lift force with the magnetic field formed as a result of these eddy currents. In this system, the magnetic field intensity and rate of change affect the lift force obtained from the eddy current. In order to investigate the effects of different parameters of the magnets to the lift force, electromagnetic field analyses were carried on by using ANSYS Maxwell software. First, we examined the effect of the number of magnets on the lift force. As expected, increasing the number of magnets positively correlated with lift force. However, due to mechanic constraints, we can increase the number of magnets and the outer diameter of the disks up to a certain point. When we consider the effect of thickness on lift force, we see that the thickness also increases the lift force to a certain point. As we reduce the inner diameter of the disk, we see that the force increases as expected, but after a certain point, there is no mechanical space enough to connect to motor shaft, and the strength of the disc decreases. In the image below, you can see the magnetic field directions of the magnets and the Halba array. As can be seen in the graph, increasing the inner diameter up to a certain point doesn't cause a much decreasing in the force as a percentage. As I told you before, increasing the outer diameter increases the force, but since we cannot determine the width of the rail, this parameter is limited. According to the results we obtained from the sensitivity analysis, we concluded that the magnets should be as thick as possible and the number of magnets, 12, is suitable for 30 degree of halba and optimum lift force. In line with the information we obtained, we designed 3 different magnet arrays which are called geometry A, B, and C. As a result of the geometry A, consisting of 12 magnets of the same size, we obtained a lifting force of approximately 250 Newton. We got a lift force of approximately 400 Newton in geometry B, which consists of 24 magnets of 2 different sizes. For geometry C, which has different dimensions but the same array, this value is 350 Newton. The relationship between angular velocity, air gap, and lift force is as shown in the figure. So in here, we create a simulation showing the eddy currents and magnetic field intensity when rotating the disks. As a result of the eddy currents that occur with the change of magnetic fields, the temporary magnetic fields cross over and create the lift force. For 3 geometry, we could obtain the 250 Newton force per disk we need. At this point, considering the easy availability of the magnets in the disks and the magnetic resistance they will create, we decided to use the geometry C. So now that we finished our design, we can get it working. We need motors and drivers to rotate the disks and a distance sensor and microcontroller to control the system. While choosing Philips Guy's 5 kilowatt brushless motor as the motor, we decided VESC as driver since it can be programmed as open source. So we prefer Panasonic sensors as distance sensors because of the sensitivity of measurement range. And due to its high frequency and being programmable via MATLAB Simulink, we used STM32 Nucleo board. In the process of mechanically realizing the system, we have analyzed the strength of connection parts that we will assemble the disk and motors on the chassis. Aluminum alloy AL7 was used as material of the fastener. We revised the design of the connection pitch to minimize the total deformation while trying to keep the mass minimum. As a result of the analysis, it was observed that the total deformation of the part we used was below 0.2 millimeters in the working range. After physically completing the system and making it operational, we continued with the control phase. The model of the system was created using the MATLAB system identification toolbox by using the force values obtained from the magnetic analyzer result of the disks based on the velocity and air gap. The controller was designed according to this model. Discrete control includes the control of BLDC motors to be controlled in the system by accepting them as independent subsystems. Each subsystem contains its own sensor measurements and controllers. However, our system has been controlled by using a centralized control algorithm with 4 disks. In the centralized control system, 4 force points are reduced to the central coordinate system, which is obtained by combining linear motion and rotational movement using geometric transformation. After that, IPD controller was designed and integrated into the system by using MATLAB Simulink. As we approach the end of our presentation, we want to show you a video that we recorded during the test and improvement period.
Değmiyor. Burası değmiyor, burası da değmiyor.
Evet, hiçbir taraf değmiyor.
So this test, which was carried out to measure the delift force, was successful. And finally, we finish our presentation by showing to you the video of our pod during levitation recorded in the Hyperloop competition held last summer. So this is Starloop team. Thank you for your attention.
Great, thanks so much. Does anybody have any questions? I actually had a question not about, oh, never mind. We will do these questions first and my questions after. Sanchit, go ahead.
So it was a very elaborate presentation. So thank you for that. My question is, you mentioned about the controllers used for. So in levitation, we are a Vegapod Hyperloop, a student team based in India, and according to our experience, we have come across the fact that levitating is not a big factor. Rather than levitating, controlling the levitation system and preventing yaw motions or pitch or heave motions is a major another hindrance. So how do you control that rather than levitating?
All right, we used measurement sensor for the just one axis levitation, and in the rail we used a mechanical component such as wheel and other axis control is not available just for now in our system. Just in one axis and for measurement sensor for the to be able to control air gap in the just one axis.
Okay, thank you.
Did I also see Damon raise his hand or no? Okay, maybe not. There's a question in the chat from Mehmet. Why did you prefer to use IPD controller rather than a non-linear controller such as sliding mode controller? Did you linearize the system or sorry? Oh yeah, ... That's how they ended it. I thought there was more to show in the thing. Oh, Mehmet, did you want to elaborate on your question a bit?
Can I answer?
For sure, yeah, for sure.
We didn't create any model of the system by using any modeling methods yet. Just we used the system identification toolbox to be able to control the system, and by doing that, we use the data from the electromagnetic analysis according to gap and velocity, angular velocity. How much force we can create force from this data. Okay, and after system identification toolbox, it's just a simple function, and we use that model to be able to create IPD controller. Okay, so when we create the model of all system, we think about that maybe we can linearize the system, and maybe we can use Lyapunov control, maybe robust control, AQR, but it's quite new department for us, and for now just we showed that the levitation system can work. Okay, thank you so much.
Awesome. I actually had a question about Technofest. I think that is something that wasn't on a lot of our radars, and so I was wondering if you could explain a little bit more about what happened at that conference, which teams were there, what happened, stuff like that.
All right. So it's the first competition of the Turkey. It was first competition, and we did all systems in maybe 3 or 4 months. And
wow.
yes, and the tunnel was ready, I think maybe 2 days ago, 2 days before competition, and we didn't test the tunnel or any subsystems before the competition, and it was very excited for us and for our team. And maybe in this year we can join the other competition, maybe in Europe, and maybe if exists United States of America or maybe Canada. So we now continue to work and develop our systems, and we hope this year will be much more better for all competitions and for our team. Thank you.
Yeah, awesome. Well, we would love to have you come to Canada at the end of May for our competition. That would be awesome.
Yes, that would be awesome for us.
Perfect.
Yes.
All
maybe
right.
This competition in that summer, and maybe we go to for joining another competition, but except I think, okay, you got it. we are quite happy to develop for this technology, okay, and in the future, in near future, we hope that thanks to this conference and lots of organization, it's going on and will be better.